We're going to eventually convert a standard form to a vertex form. But in order to think about how to do that, I'm going to start going from vertex to standard so we can see how that works. And then we're going to systematically undo it in the other direction, right? If you can go vertex to standard, then you should be able to un-vertex to standard to get what you need to do for here. It is going to require a technique called completing the square, which is perennially complicating. It causes a lot of heartburn, but never fear, friend. We will persevere. Okay, how do you do this? Well, that is just a binomial multiplied by itself. And I'm going to have to distribute these terms first. So an x with an x with a 4 with an x, and 4 with a 4, and this -5 is kicking around out here all by itself. All right, so x times x gives me x squared. 4x and 4x is 8x. 4 multiplied by 4 is 16. And I have this subtract 5 here. I'm going to have to distribute my 3. That's 3 x's. 3 times 8x. 3 multiplied by 16. Subtract 5. Nothing I can do with that. 3 8s is 24. 3 16s is 48. And subtract 5. And 3x squared plus 24x. 48 minus 5 is 43. Okay, so there you go. There's our standard form. Okay. Great. So I can go from vertex form to standard form. Now we're going to try and undo this. So y equals 3x squared plus 24x plus 43. Now the first thing we would have to undo if we were going in the opposite direction is we'd have to undo this subtraction. But without going forwards, I have no idea what number was in the back. So I can't see from this what it is that I have to add or subtract to this number to undo this particular step. And that's why this is a little problematic when you're going backwards, is because we're missing that information. These two numbers just got blended together and that information is lost. We have to kind of skip a few steps and deduce what that number was somewhere around this stage of the problem. So I'm going to go from this line, skip over that one, and look at this. So in this line, I took all of these numbers that came out of the foiling, and I put in the number in front. So to undo that, I'm going to have to pull out the number in front. Well, what is the number in front? Looking at this example, it's 3. So I'm going to have to pull out 3 from the number with an x squared, and from the number with an x, and from this number that didn't have that blended in. Now I'm not going to be able to do this part because I don't know how to separate that. but I do see the thing with the x squared, and I see the thing with the x. So I'm going to pull this number out of those two things. So y would be 3x squared, and 24 is 3 times 8. And this stupid number is just going to kick around back here, being unhelpful. All right, so I have this line looking like that line. So we're going to try and go to here. When I went from this line to this line, I was throwing the 3 into the bracket. So if I go backwards, I'm pulling the 3 out of the bracket. So my 3 comes outside. I can peel it off this x squared. I can peel it off this 8x. And this number is just, again, kicking around and being unhelpful. So I've got this looking like this. I'm just missing the third number in there. And that's where this idea comes in, is that this thing, if you follow it, it came from that. It came from a perfect square, something that got squared. But it's missing a piece. It's missing this number at the back, right? There's no number there, which means that this square is incomplete, right? There's a piece missing. So I'm going to have to stick a piece in there in order to complete this square so I can finish my process here. So this requires a little bit of deductive reasoning. I'm going to look from this line to this line. See what changed there is, instead of x squared, I need an x times itself. So let me do that. X. And this number in the middle came from 4x plus 4x. So you notice I split this in half, right? So half of 8 would be 4 and 4. So I'm going to do that here. Okay. I'm going to leave a little space there. I'm probably writing on my forehead now. This piece is missing. So where does that piece come from? Well, that piece here was this number multiplied by this number. And this number together showed up there. So I can see here that if I were to try and build these brackets like this, to get an x and an x, I'd have to have something like that. To get an x and a 4, I'd have to have a 4 there. To get an x and a 4, I'd have to have a 4 here. So the number that's missing in this back part would be the combination of the two numbers, the 4 multiplied by 4. Now, let me write that in. There. My obsessive compulsive disorder is now satisfied. It's clean, it's tidy, everyone's got space. It's great to look at. Okay, so if I put this in, right, I would have completed this perfect square. You can't just stick something in an equation. That's not allowed. So I introduced this on the right side. So that means I have to introduce it on the left side as well. So what exactly did I put in here? Well, I put in a 4 times 4. We're crying out loud. That 4 times 4 is also multiplied by 3. So I'm allowed to introduce this on the right side as long as I introduce it on the left side as well. So I've got 4 times 4 is 16, and 16 times 3 is 48. This whole structure is x plus 4 multiplied by itself, and this 43 is still hanging around, being unhelpful. Okay, now in a vertex form, wait, before we go on, that was it. That was the horrible part. That's the thing that gets people most confused, is these two lines right here. Like, what did he just do? Take a deep breath. Let me finish. We'll do a couple more examples. This will seem less sorcerous eventually. It's a bit much right now, so just prepare yourself. We're almost done. Okay, so that's what vertex form looks like. There is not a 48 over on this side. There's just the y. So I need to get rid of this. Get rid of it by subtracting it from both sides. So I'll have y equals 3. X plus 4 multiplied by itself is x plus 4 squared. And 43 subtract 48 is negative 5. Oops, we're done. So there's that number. That number I was supposed to be able to peel out of this. I didn't even think about it. Just the act of trying to find the fourth piece I needed to be able to build this structure made that number appear. So this line really, this is where the magic happens, right? Is right in that spot where you have to look at the 3 pieces you have and deduce what the fourth one is. So I'm going to clean this off, and then we'll try another example. Okay, prepare yourself. So I have a standard form. I need it to look like this, with a number here, a number here, and a number there. This number is easy. That number up front is always the number up front here. So I'm going to get that one for free. So to make this look like that, I'm going to have to factor a 3 out of this step. So here I go. 3x squared. Sorry, don't skip steps there. It makes everybody stress. 3x squared. That would be 3 tens. 64 doesn't divide by 3, so I'm just going to let it hang around out here until later when it's useful. I have this multiplied by 3, this multiplied by 3. I might as well write it like this, because both of those things are multiplied by 3, and now I can see that. This looks more like that than it did before, so we're going in the right direction. Now, this is the stage where I have to start thinking about completing the square. So I'm going to take my x and write that as x multiplied by x. I'm going to take this number and I'm going to split it in half, because that's always what happened in our factored or vertex to standard form. Okay. Now in my next line, I'm going to rewrite this, but I'm going to leave a little space. Because every time we did a bracket that was an x and a number, x and a number, x and a number, it generated 4 terms. And I only have 3 here. So I need to ask myself, what needs to go here? What would the 4th term be? So the logic is to get an x and an x. I need an x and an x. To get an x and a 5, I need 5 here. To get a 5 and an x, I need a 5 there. So what's missing? Well, the piece that's missing is this combination, the 5 with the 5, as a multiplication. So I'm going to write that in on the right. Sorry. And if I introduce it on the right side of the equation, I just have to remember to introduce it on the left. So that's a 5 multiplied by a 5. Sorry, I'm adding it in. Well, that 5 times 5 is also in the bracket being multiplied by 3. So I need to do that as well. So by introducing this term here on both sides, I have managed to complete this square. Complete this perfect square, this thing like that, because I'm going to be able to write this as x plus 5 multiplied by itself. And you notice there was no bracket squared here. There's about to be now. I had to build this. 5 times 5 is 25. 25 multiplied by 3 is 75. Let's switch back to the green here. You know what? I'm not gonna do that. I'm gonna break this apart. This big long string of things, now that I've added in the 4th term, is x plus 5 multiplied by itself. This shouldn't be here, right? There's no number in your vertex form out front. So I'm going to have to subtract it off both sides. This leaves me with 3. And x plus 5 multiplied by itself. And 64 subtract 75, which is negative 11. And there you go. So you could do this process backwards, leaving this 64 kind of alone on the end. When you get here, you're going to have to imagineer a number that would make this work as a FOIL. Balance it on the left side, because you can't just introduce something on the right. You have to introduce it over there as well. And in the process of kicking it back over here to be with the rest of the numbers, you end up generating that y value of your vertex. I'm going to erase this, and we'll try one that has a fraction in it. Okay. I see I've got a number up front, and I've got an x squared and an x. So just following the process, since this doesn't really change anything. That's 1/2 of x squared. I need to write this as something with a 1/2 up front, so I'll be able to factor that out in the next step. So half of what gives you 7? Well, half of 14 is 7, so that's what's got to go there. And this number just kicks around out back, like it always has in the last 3 examples. I can see both of these things were multiplied by negative 1/2. Ooh, careful. In order to get positive 7, that's going to have to be negative 14. And so pull out my negative 1/2. That leaves an x squared. and then negative 14x. Well, I have to complete the square on this, so that would be x and x. Split that in two would be negative 7x and negative 7x. Leave a space for my extra piece that I need to complete that square. And the 8 kicks around. So the piece that's missing here would be the negative 7 multiplied by the negative 7. And if you remember that from going from standard form to factored form, this thing with the x was the two numbers added together. The thing without the x was the two numbers multiplied together. So when you were hunting for it, you were always looking for two things that multiplied to this and two things that added to the central term. So it should make sense that you've got addition here, right? We unadded those, I guess. And that's going to be your multiplication term. Now you can't just stick this on the right side. You have to put it in over here too. So negative 7. And because it's in this bracket, it's also being negative 1/2. And we're not multiplying over there, we are adding that on to that side. Okay, so 7 times 7 is 49. Maybe do this in more than one step. Negative 7 times negative 7 is 49 plus y, and a negative 1/2. This thing, I introduced that term specifically to engineer x negative 7 multiplied by itself. 1/2 of 49, just so that we don't have anyone's head explode, just pick up your calculator. 1 times 49 divided by 2 is 24.5. And I'm going to write it as a decimal just for this example because completing the square is confusing enough. That's still there. X minus 7 multiplied by itself is an x minus 7 squared. There's my newly completed square. That's 8. And to get this over here, I'm going to have to add 24.5. Eight and 24.5 is 32.5. And I'm done. So if you can tolerate a decimal, and 0.5 is, that's okay. There's no rounding error in this, so you might as well use it. That's done. I went from standard form to vertex form. I have followed the instructions. So if you can do this, you know how to do this type of problem. I am going to go back and I'm going to fix these to be fractions instead. So let's start adding fractions in. 24.5 came from 1/2 of 49. So that would be 49 divided by 2. This would be 49 divided by 2. I added that to both sides in this line, so that's 49.2, or 49 over 2. Now here, I'm trying to add a whole number to something that's being divided by 2, and Bedmus tells me I can't do that because I'm supposed to do the division before the adding. So I'm going to have to do some factoring magic here and write this as something divided by 2. So what divided by 2 would give me 8? Well, that would be 16. So my finish here then 16 and 49 divided by 2, that would be 59/65 halves. And if you were to just check that, 65 divided by 2 is 32.5, which is what we had here as the decimal. So whether you write your answer as a fraction or a decimal, after all this, I think is probably irrelevant, as long as you're getting a decimal point that doesn't have repeats. I think we're good to go. So I'm going to have one more example where this number doesn't split evenly, and then I think we're on to the practice problems. So here we go. It's just the standard to vertex form conversion. So nothing has changed here. It looks perfectly innocent. So first thing I need to do is write both of these as 4 times something, because that's a 4. So this needs to be written as 4 times something as well. That would be 4x squared. So 4 multiplied by what would give me 12x squared? Well, 4 times a 3 gives me the 12. I need an x in there to get the x. And this thing kicks around. And that allows me to factor like so. Now I'm at the stage where I have to think about completing this square. So x squared would come from an x multiplied by an x. And this term comes from splitting that number in half. Now you might be saying, well, I can't split 3 in half. Well, of course you can. It just doesn't go evenly. So in this particular example, I'm going to write it as 1.5 so that we can get through this and see that it's manageable. And once it's done, I'll go back and try it writing it as 3 halves. So you can see it both ways. Either are equivalent. I mean, it's going to get you to the end. And you're always splitting this in half anyway. So 0.5 is a nice clean decimal. It doesn't have a mess. You're not going to have to round it. So you might as well use a decimal when you can, if you find it less confusing. So 3 would be 1.5 of those plus 1.5 of those. It's time to actually complete this square. So I'm going to write it again. I'm going to leave a space here for that 4th term. The 4th term always comes from this number multiplied by itself. So I'm going to have 1.5 multiplied by 1.5. And if I introduce it on the right-hand side, I have to introduce it on the left-hand side as well. So I'm adding in 1.5 multiplied by 1.5. And that 1.5 happens to be in a bracket that's being quadrupled, so I will have to quadruple it on this side as well. 1.5 multiplied by 1.5 is 2.25. Plus y equals 4. This hot mess here was engineered to create this. Right, x and x is x squared, x and 1.5, 1.5 and x, 1.5 and 1.5. This is still kicking around at the back. 4 times 2.25 is 9. The whole reason for engineering this was that I could write it like so. And this 9 isn't supposed to be here, so I'm going to have to subtract it off to get it back over here. -7, subtract 9, it's -16. So this particular standard form happens to have a vertex when x is -1.5 and negative 16 on the y. You maybe haven't seen that yet. The vertex has always been on some clean, tidy point. Well, there's no reason that a vertex can't be at a horrible decimal. It's just a shape, right? You can put that shape anywhere you like. So in order to prepare for that, this algebra analysis still lets you find the exact location of the vertex without having to graph it first. Okay, so that's done. Used a decimal. There were no tears or recriminations. I am, just for sense of completion, going just to go through and I'm going to write these as fractions so you can see how that works. So starting here, that's where I came across this problem where I had to split 3 in half. So instead of 1.5, I'm going to call that 3 halves. That means that every place in the rest of the solution, everywhere I see a 1.5, I should replace it with 3 halves. That's 3 halves here, 3 halves here, 3 halves here and here, 3 halves here and here. So I saw these two things, and when I generate the fourth term is always this multiplied by that, goes there. And then the correction factor you have to add to the left side is always this multiplied by this, multiplied by whatever the bracket is multiplied by, so over it goes. These 1.5s, we didn't really do any math with them after there, they just kind of followed along, so I'm just going to pop them in. And over here, 3 halves times 3 halves. When you multiply fractions, you multiply both the top and the bottom, so I ended up with 9 quarters. And if you do 9 multiply by 4 divide by 4, and these two things ended up dividing each other out, leaving just 9. So in this particular example, if you had kept the fraction in, you would have had a nice fraction neutralization happen here, and you end up with whole numbers. I think that's all I'm going to say about that. I don't want to distract from the point by putting in too many fraction issues. When you're doing standard to vertex form, you just have to pull out the a value, right? That transformation factor. Once it's out of there, you take your linear term, right? The thing with the x, split it in half. Use those two numbers to find out what the fourth piece would have to be in a completed square. Introduce it and balance it. Reverse the algebra, like reverse the foiling in order to get your perfect square, get your correction factor over here, and you're done. Deep breath. I know that's a lot, but if you do 10 or 12 of these, there's a rhythm to it, and you'll sort of get the hang of it. So with that, off to the practice problems. Good luck.